This video is on the electromagnetic spectrum and the study of light and the properties of light. So when scientists first started investigating the idea of electrons and where electrons are in atoms, their experiments led them to the study of light. Okay, so when we think of light, we think of turning a lamp on and a light bulb and stuff like that. But what we have to discuss is that there's a whole lot more to light than the light that we see. And there's actually 7 different types of light or radiation, okay, that travel through space. And that collectively is referred to as the electromagnetic spectrum. And so that's this whole idea of all of these types of radiation or light that exist. Keep in mind, these all exist, but we can only see one, and the one that we can see is visible light here in the center. Okay, all of these other ones you might know of, but we can't see them. So let's have a quick discussion on them. So of course, radio waves, that's what lets you listen to the radio in your car. Okay, microwaves are the energy, okay, or the radiation that cook your food or heat your food, I guess. Thus, the name, the microwave was named for the type of energy that it uses. Infrared, you might know infrared. There are infrared like goggles that allow people to see. It's almost like heat sensitivity, and so they use them for locating people who maybe are in the woods or things like that. Visible light, of course, is all the light that we see, and that is made up of the colors of the rainbow, and they are red, orange, yellow, green, blue, indigo, and violet. And so we we give the colors of the rainbow an acronym that is Roy G. Biv, and that doesn't mean anything. That just stands for the colors of the rainbow. So red, orange, yellow, green, blue, indigo, and violet. Okay, so then past visible light, we encounter ultraviolet. That comes from the sun, and you might know that sunscreens will advertise that they protect against UVA and UVB rays, which are 2 different types of ultraviolet light coming from the sun. X-rays, of course, we all know, we've all had an X-ray, even if it's just our teeth at the dentist office. And then gamma rays. Gamma rays are used for radiation therapy in cancer patients or getting rid of tumors, things like that. So as you might guess, this end of the spectrum is the high energy end. So I'm going to go ahead and label that on my paper. That's going to be important to us as we progress through this discussion. So the high energy end includes like X-rays and gamma rays, whereas the low energy end is on the other side. Oh, I want to have room, so let me do this. Okay. So after this discussion so far, you should be able to answer questions like this. Which type of light has a larger energy? Microwaves or ultraviolet waves? And of course, looking at this, here's ultraviolet, here's microwaves. So obviously ultraviolet have a higher energy. You should also be able to answer the question of which color of light has a higher energy? Yellow or blue? Okay, so here's yellow, here's blue. Blue being closer to this end of the spectrum means that blue would have a higher energy. Okay, so questions like that you should be able to answer so far. So from here, we go into a little bit of a discussion of light in and of itself. And so we're going to learn that all light travels through space like a wave. And you might be familiar with this depending on what math class you've taken. Maybe you've studied this a little bit. So we're going to draw a wave. Okay, which looks like this. And we're going to label a couple things about the wave. So the first thing we're going to label is the peak, okay, of the wave, which is called the crest. We're going to talk about what the height of the wave is called. This is called the amplitude. Okay, basically it's the height of the wave. And then two pieces of information that are very important to us. And one of them is the distance from one crest to another crest. And that is called the wavelength. Okay, so I'm going to come over here and define wavelength. Okay, and wavelength gets a Greek letter variable, which is the symbol lambda, and it kind of looks like a diagonal line and then a little curve. Oops. Okay, so that is the Greek letter lambda. I put it in parentheses for you. And so instead of like a variable w, okay, it gets a Greek letter lambda. And wavelength is defined as the distance between two crests, okay? And the units for wavelength, it is a length, okay? And so the units can be any length unit. It could be meters, it could be centimeters, it could be kilometers. Most often we'll see it in nanometers, okay? And there's a conversion factor for that, which says that there are 1 times 10 to the 9th nanometers in a meter. I think that's a billion. Is that a billion? It's a billion. So there are a billion nanometers in a meter. So the nanometer is very small. Okay, so that is the wavelength. So knowing that that's the wavelength, let's come up here, back to our picture, and see I drew this wave for you, okay, right here, traveling through space. So now that we know wavelength, we can label which side of the spectrum has a bigger wavelength and which side of the spectrum has a smaller wavelength. So over here, on this end of the spectrum, we see that the wavelengths are pretty big. So this is, let's say, large wavelength, and I'm going to use our symbol so we get used to it. And this is small or low wavelength, okay? So again, after this discussion so far, you should be able to answer a question like, which has a smaller wavelength, I don't know, violet light or infrared, okay? So smaller wavelength, here's infrared, here's violet, embedded in visible, and so that would be violet because it's closer to this end of the spectrum. Okay, and nothing that we've memorized so far, we've just learned these terms and we're labeling our spectrum. Okay, so there is a second piece of information that we have to keep in mind, which is something called frequency. Now, frequency is kind of interesting. Frequency gets the Greek letter nu, and it looks kind of like a cursive V. Okay, that is the abbreviation for frequency. And frequency is defined as the number of crests that pass a point in a given amount of time. Okay, so that might be like if I drew, okay, here, let's do wave A and wave B. Okay, so first of all, let's talk about the units for frequency. Frequency units are weird because they do involve a time, but it's frequency in and of itself is not a time. Okay, it's the number of crests that pass that point in a certain amount of time. So actually frequency is kind of weird, and most of the time we see frequency units as 1/seconds, okay, which can also be written as seconds to the -1. So it's not seconds, it's like waves or crests per second, okay, and there's a difference between those two. So if we look at my wave A and my wave B, and we think about how many of these crests, okay, in this wave would pass a point in a given amount of time versus how many of these crests would pass that same point in that same amount of time, wave B is going to have a much larger frequency, okay, because there's more crests passing that point, which would mean that A has a smaller frequency. However, let's go back to this idea of wavelength, right? A's wavelength compared to B's wavelength is much bigger. So while A has a small frequency, it has a large wavelength, okay? And while B has a large frequency, it has a small wavelength. And so this is where I want to introduce something very important to us at this point in time, which is the idea of a relationship being inversely proportional. And that is, an example would be as wavelength increases, frequency decreases, okay? And that's an inversely proportional relationship. This is a really big idea. Okay, so if we go back up to my chart here, we can now add a third discussion, which is the discussion of frequency. So on this side of the chart, the crests are really close together. So this is going to be a large frequency. I almost forgot its symbol. And on the other side, this is going to be a small frequency. So we have a couple relationships here that we can establish. We've just established that frequency and wavelength are inversely proportional. So are wavelength and energy, right? Look, small wavelength, big energy. So let's write that as an example. So as wavelength increases, energy decreases. Okay, that's a second inversely proportional relationship. But there's one hiding up here that's not inversely proportional at all, and that is this one. And I can go to either side here, but with a low energy or a small energy comes a small frequency. Well, that's something called directly proportional. And so directly proportional means as one gets bigger, the other gets bigger, or as one gets smaller, the other gets smaller. So that's as, let's see, wavelength, we can do increases. Nope, that should be frequency. Sorry. Oops. As frequency increases, energy increases. Okay, you could also say as frequency decreases, energy decreases, because that is also true. Okay, so I need to give myself some more room because I did not give myself enough room on this. So hopefully you have enough room on your paper. So I'm going to skip this practice, which comes later for you anyway, and continue this discussion under the study of light. Okay, so we've learned these relationships, and now we want to learn a couple things about light, and that is that all light travels through space at a constant speed. Okay, and that is the speed of light. The speed of light is given the symbol c. And the speed of light is 2.998 times 10 to the 8th meters per second. It's very fast. From here, we figure out that there's another relationship that we can talk about, which is the relationship between wavelength and frequency. We've just learned that they're inversely proportional, but now we have a formula. And the formula says the speed of light will always be equal to the wavelength times the frequency. Okay, so the speed of light will always be equal to the wavelength times the frequency. Keep in mind, you know the speed of light, it's a constant, it's this number all the time. So if we know c and we know, let's say, the wavelength of light, we can always find the frequency with a little bit of algebra. And so that's what we're going to be doing in this chapter. Now there's a second formula that relates energy into the mix. And so a second formula says that the energy of light can be calculated with this formula. Okay, where E is energy, nu is frequency, okay, measured in the unit of 1/second, and H is a constant, and it's called Planck's constant, and it is this number, 6.626 times 10 to the negative 34th, in a unit of joules times seconds. Okay, so then what happens is if we take joules times seconds, times 1 over seconds, your seconds cancel, leaving you with an energy unit of joule. And the joule is a unit for energy. So now we have 2 formulas that have come out of this, which are going to be important for us. We also have 2 constants, okay, H and C. And now we're going to look at how we can use these to solve a couple problems. And this, again, is just an intro. We're going to be doing a whole lot more practice with this as time progresses. Okay, so list 1 similarity and 1 difference between microwaves and gamma rays. So, well, they have different lots of things, okay? They have different energy values, they have different wavelengths, they have different frequencies. Okay. In terms of what's similar, they travel at the same speed, and a lot of students often say, you know, they're invisible to us, which would be a similarity. So that is fine if you thought that. Okay, so those are some good answers for that one. All right, number 2, here comes the math. Calculate the wavelength of yellow light if its frequency is 5.10 times 10 to the 14th. Okay, so I go look at my formulas, and I was given a frequency, and I want to find a wavelength. Well, the only formula that makes sense here is this one. Okay, so I'm going to come back up here and write C equals lambda times frequency. So I'm being asked to calculate the wavelength. So I want wavelength, which means I need to know frequency and C in this case, and I do, because remember, C is a constant. So I need to solve this thing for lambda, get lambda by itself. I'm going to divide both sides by frequency, giving me a formula of C divided by frequency. And now I just plug my numbers in. So remember, C is a constant, right? It's right here, 2.998 times 10 to the 8th meters per second. And my frequency was given to me in the problem. Seconds over 1 or 1, seconds to the negative first or 1 over seconds. Okay, let's have a unit discussion here. My seconds actually cancel. And that's going to leave me with the unit of meter, okay, which is fine for a wavelength. Now let's talk calculator usage. So I'm going to dual screen here with my calculator, if I can get it to work. Whoop. I have such trouble. You guys are so much better at this than me. There it goes. Sheesh. Okay, well, I didn't dual screen, but that's okay. So I want to do this math. So I'm going to type. Remember that I cannot use times 10. So actually, I'm going to put this in parentheses just to be careful. So 2.998. Remember, I do second, the comma button to get that E button. And then I'm going to enter the exponent of 8. And that's my numerator. So I'm going to close my parentheses. And then I'm dividing by the denominator, 5.10 second, comma, to the 14th power. And I'm going to hit enter. Now, this calculator gave me a crazy answer in scientific notation. Let's talk sig figs for a second. So we're dividing, so number of sig figs. So I have 4 sig figs in this number. I have 3 sig figs in this number, which means my final answer should have 3 sig figs. So I'm going to record this as 5.88 times 10 to the negative 7th. And remember, we have decided that my unit was meter. And that is my answer for number 2. All right, and we have one more. Red light has a wavelength of 650 nanometers. Calculate its wavelength in meters. So this is just a conversion. So 650 nanometers. A little bit ago, we learned, where was that? Up here? Yeah, right here. Here's the conversion. That in 1 meter. Oops, did I write that already? Okay, that in 1 meter, there are 1 times 10 to the 9th nanometers. So like I said, this is just a conversion. This is not a... There we go, I just dual screened it. This is not a math problem really at all. So here we go. So 600, or it's not a like an algebraic problem, it's just conversion. So 650 divided by 1 second e to the 9th power, and I get 6.5 times 10 to to the negative 7 meters. So that's my answer for the first part of calculating that wavelength in meters. And now I want to find the energy of red light. So I'm going to get rid of my calculator for a minute. Because I want to show you something that I haven't shown you before, which is there's a third formula for that we can learn. And so here's the problem with this one. So it says calculate the energy of the red light. Well, I have a wavelength. Okay, so I need an energy, need to find an energy, and I only have a wavelength. So this is a little bit problematic because my energy formula, right, says that I need to know frequency. Well, I don't know frequency. So let's think about this for a minute. But I do know wavelength. So I'm actually going to derive a new formula for you. And I'm going to take this speed of light formula and solve it for frequency. Okay, so I get that, I'm going to write it down here. I get that frequency is equal to the speed of light divided by lambda. Well, then I have this formula that says energy is equal to H times frequency. But see, what I've just done is solved for frequency in terms of lambda. So what I'm going to do is insert this in place for frequency. And all of a sudden, I get a formula that looks like this. And so this is the formula that's going to be the best one for me to use if I want to find energy when I'm given wavelength. And here's how we're going to do it. Okay, so H is a constant, 6.626 times 10 to the negative 34. Units are joules times seconds. Remember, none of that needs to be memorized. It's just a constant that will be given to you. Times the speed of light, meters per second. Notice I'm putting units on everything. And then my wavelength, 6.5 times 10, what was it, to the negative 7 meters. Now let's have a unit discussion here. Look what happens. Meters cancels, seconds cancels, leaving me with a unit of joules for energy. And that sounds good. We just have to do the math. Oh my. Okay, so here we go. So the math, and I'm going to do this all in parentheses again, 6.626 second EE. Oh, nope. Okay, try that again. Second EE, there we go, to the negative 34 times, oh, no, go away. Oh man, sorry. I lost my calculator. Okay, there we go. Times 2.998 second, comma, 8. Okay, now I'll close my parentheses and then divided by, just do parentheses just to be safe, 6.5 second EE to the negative 7th. And let's hit enter. And so I have, again, lots of sig figs, but according to my answer, let's see, I should have 2. So we're going to call this 3.1, right? 3.1. Oh, I can't write on the calculator. Times 10 to the negative 19. And that is my answer for the energy of this light. So that was a quick lesson. We're going to do much more practice in class, but that is your intro to the electromagnetic spectrum and calculating wavelength and frequency.